Okay, today in class we studied the gas laws, we read aloud, we used our reading sheets on page 4 is where it started from last week. So what we did is we highlighted this section here, so if you want to pause the video and highlight the section, don't go to Boyle's Law, and then we'll take notes over that section. So pause the video, read those silently or aloud, and highlight the important information, and then come back, press play to resume the notes. Okay, this is what our notes look like. Here's our essential question for today. So I'm going to go through these kind of quickly, but you can just pause the video if you need extra time and rewind it and watch it again. So gas laws notes is our title. Our EQ today was how do gases behave as their pressures, temperatures, and volumes change. And then the first thing I did is we talked about gas characteristics. And again, these are all from your reading. And the very first thing is gases are compressible. Okay, gases are compressible. Compressible, remember, can be compressed means that it can be squeezed in together. I just did a little arrow here and said they can also expand because that is also true. It doesn't, compressible doesn't necessarily mean expand, but because they can expand and spread out, they are also, by reverse, squeezed in or compressible. So that's just something to think about. And then particle movement. Particle movements, they move randomly in straight lines, and they bump into other particles and they bump into the walls. So they move randomly in straight lines, so they go here and they bump off the wall, and they go back this way, they ricochet back, and they go this way, and they go back, and they go this way. So they aren't moving in curlicues and like a butterfly flies all over the place and just at random motion. They are random, but they are moving in straight lines. So that's something to think about. When Miss Guy was in my room, we talked about like a air hockey table. So that air hockey puck, when it hits the side, it bounces back, it ricochets back, and kind of that movement and that motion is something that you can think about there. Bumping into those walls when you're talking about a gas inside of a container of some sort, when it bumps into the walls of the container and bumps into each other, it creates something called pressure, and that's a force. This is a force called pressure. And then pressure is measured in atmospheres, ATMs. And what an atmosphere is, to think about, is 1 ATM is the pressure of the air at sea level. We are approximately at sea level. We're above sea level, not by a huge amount though. So the air pressure, you could say in our room, you know, when you walk outside, it's about 1 atmosphere of pressure, give or take. And then also too, just kind of to summarize, there's a lot of space between the gas particles. So that's space, and again, that's why it's compressible. That's why we can squeeze it in. Now, the second thing that we did in class today is we flipped over to page 5, and we did the same thing. We read and we highlighted this information about density. So if you want to pause it and complete density, we'll do that. And now these are the notes about density. The density of a gas. Remember, density is not a new idea. We've talked about it. You talked about it last year. You learned it probably for the first time about 6th grade. This specifically you probably learned when you learned weather and weather patterns, and you learned about air masses. So the density of the amount of particles is the amount of particles in a given space. So I drew these 3 little pictures. My boxes are not identical, the same amount, but they're meant to be. I'm not an artist, but those boxes are about the same given space. So the given space is the same. And so if I have more particles in that given space, then obviously it's going to be more dense. If I have less particles in that given space, then it's less dense. And you know, this is somewhere in between. Now, when you learned about this in 6th grade with weather, just to give you some examples, some real world examples here, the colder temperatures are going to look more like this, colder air masses and stuff, because as the temperature drops, you know, the molecules slow down, they actually contract, they get closer together in the gas, and so it becomes more dense. And so cold air masses are known to sink down towards the ground, where least dense air masses are actually going to have warmer temperatures. So the warmer the temperatures are, the farther apart those, because remember the temperature is making those particles speed up and they spread out. So it's going to become less dense. And so hotter air masses would actually, if those two air masses met, the warmer air mass coming from this side would actually be less dense and float on top. And then I'm not sure exactly what type of weather pattern you would have at that front. I know there was, I learned it in 6th grade too, I can't remember, but once the coldest should sink under the warm. And you'll have some type of weather. I don't know if that's the tornadoes and the thunderstorms and things like that that's going to happen when those two air masses meet. But anyway, you get the picture. But that's what happens here. Now, to calculate density, you actually can do a little math calculation, which is mass divided by volume. So there's our formula. Again, this is nothing new. You've been calculating density probably since 6th grade, but I just want to show you, here's a comparison, because particles, when we're talking about particles in a given space, how they match up. So particles are your mass, and your given space is your volume. So this is just a mathematic way to say what that definition is doing, and we put numbers to that, and that's where we can get a density from. And then when we calculate this, we of course have to have a unit. We have to have those scientific units on there. So I would have the density of a gas would be a gram per liter. The reason they don't do it per milliliter is because gases are a lot more spread out and take up a lot more space than like a liquid. But your gram is your mass unit, and your liter is your volume unit. So that is why your density is going to have a grams per liter. It's going to have basically two units, because it's a comparison of those two. And then I just summarize those. So the closer the particles are, then the greater the density is, and that just goes back to summarize what my picture says. So if you need to pause that to complete those, you absolutely can. Then what we did is I have a chart, and you can get the chart from the orange crate if you don't have one. I'll put the extra ones in there. But we read the laws, and the laws start on page 4 with Boyle's law. And Boyle's law looks something like this. You look on page 4 and read this little paragraph here. But Boyle's law states that for a fixed amount of gas, so you got a certain amount of gas, right? Let's say we have 10 particles of gas, 10 particles. At a constant temperature, let's call it 50 degrees Celsius, doesn't matter. 10 particles, 50 degrees Celsius, that's staying the same. So the volume of the gas increases as the pressure decreases. When we look at these relationships, if something's increasing and the other thing's decreasing, those two can be compared in what's called an inversely proportional relationship. They're inverses of each other. Also means opposite, right? But the grown-up word for that is inverses. So my volume is increasing and my pressure is decreasing. So when I filled in my chart here, I'm going to leave off density for just a minute. What this Boyle's law is saying is this. The temperature's constant, okay? As the volume, it said this part first, as the volume increases, the pressure decreases. So the opposite is true. If the volume decreases, the pressure increases. So those two are inversely related. They're opposites, so they're inverses of each other. Then we have to think about what this means for density. So density isn't part of the law, but our standard in the state of Georgia wants us to learn and think about, well, how does that affect the density? Well, if I have the same amount of particles and I'm cramming them into a small spot, and I'm increasing that pressure there, I'm squeezing them in, thinking about trying to put a pill in a Ziploc bag, think about that, you're squeezing all that into a smaller space. That's actually going to be more dense. You're going to increase that density there, okay, because you're squeezing more particles. Remember the particles that we just drew. And then the opposite is true. If I increase that volume in a gas, it will escape. It will spread throughout the container. So it will actually decrease the density there. Those particles will spread out. So then if we read the next one, it is about Charles's law. Okay, so Charles's law is on page 5 here. And so you can read this part up here. But Charles's law says for a fixed amount of gas, still we're talking about fixed, at a constant pressure, so the pressure is staying the same, the volume of the gas increases as the temperature increases. So what this means is this relationship right here.
Zaya Andrews, please return to Mr.
So our pressure, it said, was constant. And this is a directly proportional relationship. We have temperatures increasing and volumes increasing. temperature's decreasing, volume's decreasing. And then so what does that do to the density? Well, think about it. We've got faster moving particles. They're spreading out. They've got more room to do it. So what that's going to do, it's going to have very, very low density. And then the opposite is true. If we decrease the temperature, remember those particles come together, decrease the volume, it takes up less space, and that's actually going to increase the density. It's going to become more dense. And I put over here hot air balloon. I didn't talk about the Coke bottle there. I'll go back and talk about that, but let's talk about hot air balloon right here for Charles's law. A hot air balloon works this way. So you've got a trapped amount of air in that hot air balloon. Even when it's on the ground, there's a trapped amount of air. So when they turn on that flame, they're not adding air to it. What they're doing is they're increasing the temperature, which makes those molecules spread out and fill the whole volume of that balloon. And so what happens is that air inside that balloon becomes less dense than the air in the environment that day. And so if something's less dense, it's going to float, so that it's going to actually rise above and it's going to fly high. So when that balloon's ready to come and park it, what they're going to do is they're going to decrease the temperature. Those particles are going to squeeze in and contract, and that balloon is going to become more dense, and therefore it's going to sink. Okay, so that's that law. Let's go back and talk about the Coke bottle right here that I didn't talk about. But this is talking about, let's say, with pressure and volume. All right, so a Coke bottle is pressurized when it's closed. You've got a squeezed amount of gas. You've carbonated that soda. We're not talking necessarily about the liquid, but we're talking about the gases that are dissolved in the Coke itself. And so you've got high pressure. So the Coke bottle's pretty tight when you buy it. Hopefully when you crack it open, it goes pshh. So what happens here is if you increase the pressure under smaller volume. So I've crammed a lot of CO2 gas when I'm at the Coke bottling plant into a really small volume. Okay, and that's what keeps its freshness and keeps it bubbly and all that good stuff. But if you leave that open, what's going to happen is the pressure inside that bottle is going to decrease, of course. You know, you can squeeze that bottle now when it's open. And those gases are going to start to increase in their volume. They're going to spread out and they're going to fill up the room. Of course, you know, your room's not going to fill up with Coke fumes, but they are going to spread out and what they would call disperse or dissipate throughout the gases in the room. So they are not going to stay in that bottle. They're going to escape. And so that's what's happening here. Okay? And then the last law is also on page 5. It's Gay-Lussac's law. And so Gay-Lussac's is here. It says for a fixed amount of gas at a constant volume, the pressure increases as the temperature increases as well. So this one, with Gay-Lussac's, on this one here, the volume stays constant. Okay, that's what we're looking at. The volume stays constant. And you're comparing the pressure and the temperature. Okay, I think about things like in a can or a football or a basketball. Things like that are your volume's kind of fixed. A tire to a car. Your volume of that tire, let's just think about tires of cars, is kind of fixed. Okay, it is fixed because your tire on your car can only get so big before it pops, right? So we're looking at, you have tire pressure, of course. In the summertime, and the wheels turning on the car and you're traveling at high speeds, all those things can increase the temperature of the gases inside those tires. And when you do that, you're also increasing the pressure. In the wintertime, or if there's a cold snap, it's happened to me on my car, the temperature drops. I actually will get a light on in my car that says tire pressure is low. And so when that happens, those air molecules, remember, they've contracted and they've squeezed in closer together, and so my pressure is going to drop. And so how that affects density is not directly related to the pressure here like it was up top. It's related to that temperature. So think about what those particles are doing. The particles are speeding up, they're spreading out, so the density is actually going to drop there, even though the pressure is increasing. High pressure, high temperature, but your density would be lower than one that had a lower temperature, because the density would actually increase there. Okay, and that's what we're looking at there. So that's your Gay-Lussac's law. All right, so that gets a little bit confusing, and I'm not really, I'm sure there's some, this part there's no changes to, but I think, right here with the density, it's a little bit vague. But again, density is not part of the laws, okay? However, it's affected by that behavior. And again, it's not part of the laws, but the state of Georgia did put it into our standards. So we do need to address that kind of behavior and what it says. You notice it says here, you will not be asked to memorize which law says what, but you will be asked to apply these behaviors to actual situations. So I'm not going to say, or the state is not going to tell us what's Boyle's law say, and you just got to fill it in. It's not going to be like that, but they would say, you know, if you have a gas at a constant temperature with increasing pressure, what's going to happen to the volume? Well, the volume would decrease. Okay, so this is a chart you're going to have to study. You know, it's tricky. You've got to study it, look over it, come up with devices that are going to help you memorize what's happening here. And again, I would focus on these three. Don't worry so much about density, because density is related right here to volume, and in this one the density relationship's a little questionable, I guess you could say. So I'm going to upload these. Well, they're uploaded. And then we will do the phase diagram worksheet. If you will watch the tutorial for this sheet, and this sheet's in the orange box. And what I ask the students to do is to go through and try to complete this front and back, just reading the graph. And if you watch the tutorial, that should help you with this sheet. This sheet is, again, is in the orange crate if I did not get you one, or if you don't have one.